So because amino acids are just that, amino acids, they have both acid and base properties. So what do these properties come from? The amine group generally acts as a base and can pick up a hydrogen and thus bear a positive charge in the end when it picks up a hydrogen. And a carboxylic acid group can lose a proton or hydrogen, and then it will bear a -1 charge when it's lost that hydrogen. So it has both acid and base properties if it isn't connected to a protein backbone. But even the R groups themselves can also bear acid or base properties depending on what that R group is. And so sometimes we even have three things to consider when considering the properties of amino acids. So we'll have an amine group that can be basic and it can gain a hydrogen, making it a +1 charge, or it can lose that hydrogen to become neutral. And a carboxylic acid group that if it has the hydrogen on it, it will be neutral, and if it loses the hydrogen, then it will have the -1 charge. So we can see that here. At low pH, we have the form of this amino acid, which just has a generic R group, where it has a +1 charge on the amine and no net charge on the carboxylic acid group. And so let's go ahead and define what these groups are, because it may be a little hard for you to see that from the ball and stick model. So we've got our alpha carbon here, and our nitrogen here, and our carbon here bearing the OH group. Okay, and so this nitrogen has 3 hydrogens. And if nitrogen has 3 bonds, then it's going to have a +1 charge, okay? And our carboxylic acid group still has its hydrogen on it. So this is at low pH. We've got extra H plus in solution, and that H plus that is in solution is going to be pushing hydrogens onto the groups that can bear those protons. And so our NH, what would be neutral, a neutral NH2, let's go ahead and draw that, an NH2, okay, is going to have a lone pair that can pick up a hydrogen from H3O+, okay, and then it gains this +1 charge, and it'll be in this form right here. So that's going to give the overall molecule a +1 charge because the NH3 has a +1 charge. So at a low pH, we have a net charge on that amino acid of +1. Not considering what the R group may have. The R group may also have a charge, but we're not considering that at this time. So as we increase the pH, what's going to happen? Well, we have a pKa for this carboxylate group, which we're going to look at later on. It's a pretty low, and so as we go beyond that pKa, we're going to begin to lose this hydrogen here. And so as we do, when we fully deprotonated all of these carboxylate groups, okay, we're going to have this species. And so our amine group has a positive charge. The carboxylate group has a negative charge, and therefore the net charge on the molecule will be neutral. When the net charge on that molecule is neutral, this is called a zwitterion. Zwitterion means that it has 2 charges, so it becomes neutral, or it's in a net neutral charge. Okay. And so then as we increase the pH, we can begin to lose one of the hydrogens on that NH3, and as we do, so we see the what's happening is this hydrogen's going away. Of course, we know something's pulling it off, like water in the system. And so then that NH3 becomes an NH2, okay, and our carboxylate is still COO, so it's negatively charged, and therefore we have a neutral on the amine and a negative on the carboxylate, which gives this amino acid a net -1 charge, okay, at high pH. Alright, so we're going to be looking at a lot of different examples of that type of thing in this section of the chapter. So amino acids are weak polyprotic acids. Okay, so because if we're starting out at low pH, because this NH3 then can act as an acid and give up its hydrogen. If it's an NH3 plus, it's going to be an acid itself, and so it's going to give up its hydrogen at its certain pKa value. And so also we have the carboxylic acid group, which is also an acid. So why is it a polyprotic acid? At least all amino acids are going to have the possibility to have the NH3 plus, and then they have the alpha carbon, and then they have the COOH, and so they can lose a hydrogen from here and a hydrogen from here. Okay, and they also may have an R group that may also be charged that may have a hydrogen that it can donate as well. So they are polyprotic acids. And the degree of dissociation depends on the pH of that medium. So for amino acids which do not have a dissociable side chain, the first which means that R group does not have a hydrogen on it that can be donated. So then the first dissociation is that of the alpha carboxy group, which has a pKa of around 2. So what does that alpha carboxy group look like? Like we talked about before, the first dissociation is going to be, this is our alpha carbon here. We've got an amine that has, at this low pH, 3 hydrogens. So we're talking about, we're going to start out at a low pH, and then as the pH increases and we go through that pH of 2, we're going to start losing this hydrogen here. Okay, and so that's why is this H2A plus. So this might be a little bit confusing in its generic form. So we have this hydrogen here that is one of our H's in the H2 and one of the hydrogens on the nitrogen. So that's where our H2A plus comes from, because this nitrogen is positively charged because it has 3 hydrogens on it, and therefore it's going to be able to lose that hydrogen eventually, so it is a dissociable proton. So it's positively charged, the overall molecule, because our carboxylic acid is neutral and the amine is positively charged. So we have H2 because we have both of these hydrogens which can be lost. The acid is, just the, it becomes the conjugate base of the acid itself. That's what our A stands for. So basically the rest of the molecule that I don't have circled in red with those 2 hydrogens on it, it all has a +1 charge. Then when it can react with water, the first dissociable proton is going to be this one here. Okay, so the one on the carboxylic acid group. And then once it loses that hydrogen, okay, then this is going to become negatively charged, the oxygen will, and so since we have a positive and a negative, they cancel each other out. So now we still have, let's get a different color here and see if we can define this a little better. So now we still have one dissociable proton, okay, but since we have a negative and a positive charge, at this point we have HA, okay, but it's 0 charge because we have that Zwitterion form. Okay, and then we have H3O plus that was formed. So we can write a Ka1 for this reaction where we're losing that first hydrogen, okay, where we have our products over our reactant. Okay, so again, for amino acids that do not have a dissociable side chain, the second dissociation is that of the alpha amine. Okay, so this amine is called the alpha amine because it's attached to the alpha carbon. And remember, we already lost our hydrogen off of the carboxylic acid group, so we've got this species right here as we go into a higher pH level. And so this is our HA0 because it has one dissociable hydrogen. It's going to react with water, okay, to give us the A minus at this point. Remember, we started out with H2A in the previous slide, okay, and that was positively charged. And then we ended up with this HA0, which we're starting with in this slide. This is our HA0 here, okay. And now we have, once we lose this hydrogen on the amine, we're going to have A minus. We've lost both of our dissociable protons, and we have also then H3O plus we've generated. So we get this Ka2, which is our products over reactants. So let's see what the pKa's look like for these dissociable protons. That of the carboxyl group is a pH of 2. The amine group is a pKa of around 2. So around pH of 2 it will be 50% dissociated. The amine group is going to be a pKa of around 9. So at 9 it's going to be about 50% dissociated. These numbers are approximate, but you know, it's good enough to kind of remember that as a rule of thumb. So let's see what a titration curve might look like for an amino acid like glycine. Remember glycine? You need to learn these amino acids has just a hydrogen for its R group. Okay, and so that's a simple one. That's the simplest one. And if we start out with a low pH, we're going to have a positive charge on that nitrogen. Remember, we got these H pluses in solution at low pH. That is not going to be a plus. There it goes. Okay. And we're going to have everything protonated. So, protonated carboxylic acid group, protonated amine group. And so we start out with the protonated amine and carboxylic acid at low pH. So if we have a pH of about 0, then we're going to have both of those protonated. And then as we move to the right, let's say we add equivalents of OH minus. Okay, so we add equivalents of hydroxide. When we add a half of an equivalent of hydroxide, we're going to be at about a pKa of 2, which is our first pKa, where we're going to lose this. Let's get a different color. That might not work. Okay, where we're going to lose this hydrogen, so it's going to be 50% deprotonated when our pH is equal to the pKa. So if we add a half of an equivalent, we're going to be at pKa 1. And then if we add a whole equivalent, what's going to happen? We're going to fully deprotonate this carboxylic acid, which means we're going to fully have this species here. Okay, but we still have the amine protonated. So then that's called our isoelectric point, because the positive charge of the amine balances out the negative charge of the carboxylate group. So we have at this point, let's go ahead and erase. At this point we have this species here. Okay, we have positive and negative balancing each other out. That's called the isoelectric point. That's a very important word we're going to be using a lot. And then as we move through pKa2, okay, that means we have 50% deprotonated this hydrogen, or one of those hydrogens from the nitrogen. We don't know which one, doesn't matter, right? So we've added 1.5 equivalents of base. That means our pH is equal to pKa2. And then as we continue to add base and we go up to 2 equivalents, then we fully deprotonated our glycine, from which one of the hydrogens has been removed from the NH3+, and all of the hydrogens have been removed from the carboxylate group. So now the carboxylate group has a negative charge and the amine has a neutral charge, which gives our charge on the molecule a -1. So on the left, our glycine has a +1 charge. In the middle, it has a 0 charge. And on the right, it has a -1 charge. And we can see how that's affected by adding equivalents of acid and base. So if we start out on the left over here, and we add 1 equivalent of base, we're going to end up at our isoelectric point. And when we add 2 equivalents of base, we're going to fully deprotonate both of those protons, because this is a strong base and we have weak acids. Now, if we started out at the isoelectric point and then we added one equivalent of acid, then we would fully protonate that first carboxylic acid group, so it would gain the hydrogen, okay? If we started out at our isoelectric point where we had this species here and we add one equivalent of base, then we deprotonate our amine. Alright, and so if we start out with the -1 species and we add two equivalents of acid, then the first hydrogen we're going to put back on is going to be this one on the amine. We'll get this species. The second equivalent is going to put our hydrogen back on the carboxylic acid. And so we'll get this species. So you can see how adding acid and base is going to affect the charge on the molecule. So these are some common pKa values. You might want to print this chart so you'll have it handy. So the pKa for the alpha carboxylate group, that's the carboxylic acid group that's on the alpha carbon, is around 2 for all of these, but you can look up that exact pKa if you want to do some calculations. We're going to do a couple of calculations in a bit. And so for the alpha amine group, our pKa is usually around 9 or 10, okay, depending on which one we have. And then the R group can also have a pKa. Now, not all of them do, because not all of them have dissociable protons. But if they have a dissociable proton, that means even if the side chain is a base, if it can pick up a proton and lose that proton at some point, or if it's an acid so that it has the proton on there, and as we increase the pH, that proton's going to be lost, then it's going to have a pKa. And so these groups that have a pKa where that hydrogen can be removed, then they will have this number. But if they don't have a dissociable hydrogen, like for example glycine, then it's not going to have a number here. Alright, and so you should know the pKa values for these R groups, or at least print them out and have them handy. Because if you're going to be taking your tests online, then you can use a chart, but next semester you may not be taking your tests online, or if you're in somebody else's class and you're just watching this video, you probably need to memorize these pKa values because you may need to have them for your exam. So Arginine has what's called a guanidino group. You can go back and look at your amino acid chart and look at that side chain group there. That has a pKa of about 12.5. Aspartic acid is the carboxylate group at 3.9. Cysteine is that sulfhydryl or SH group, which has a pKa of around 8.3 to lose that hydrogen. Glutamic acid is another carboxyl group at 4.3, and histidine has an imidazole group, which has a pKa of about 6. So you'll probably need to learn these groups that are attached to these amino acids and memorize these pKa's, especially for next semester. But for this semester in my class, you will be able to use a chart if you're taking this in fall 2020, because we're doing this online. If you're not doing it online, then that may be different. Here we have lysine, which has an amino group, which has a pK of 10.5. Serine, which has a hydroxyl, which is around 13. Think alcohol. Threonine, which also has a hydroxyl, a pKa of 13. And tyrosine, which is a phenolic OH. So you'll remember that phenol has a lower pKa because of resonance at around 10.1. So if we look at the titration curve of these polyprotic amino acids, you can see that the first pKa's are dealing with the loss of the alpha carboxylate or the alpha amine group, and then we start losing the hydrogens off of that side chain. Okay, so for this one we have glutamic acid, okay, GLU. And so looking at the structure of the molecule, here is our alpha carbon, okay? And so the first one that we're going to lose is this COOH here. Remember, that's a carboxylic acid side chain. So we have our I'm just going to draw this. I like to look at amino acids like this. Okay, so our R group is this thing right here. Okay, and we have a dissociable proton here. So the first proton that we're going to lose, we're going to see a pKa for that one at around 2, and that's going to be our alpha carbon carboxylic acid hydrogen right here. Okay, this hydrogen right here. The pKa is around 2, and so then we're going to completely remove that hydrogen, and when we do, we still have the positively charged amine group. Okay, this was positively charged. And so that's going to be our neutral species. And when we reach our neutral species, we are at the isoelectric point. Okay, so if we add one equivalent of hydroxide, we reach that isoelectric point. Okay, then we go through pKa2, where we're going to start removing. Oh, I'm sorry, this one, actually the second pKa that we're going to go through is this hydrogen here. Okay, so the second pKa is this one. So now we have a +1 charge here, a -1 charge here, and a -1 charge here. So these two guys, let me go ahead and get a different color. These two guys are going to cancel each other out, +1 and -1, and we have -1 here. So that's going to give us an overall charge on the molecule of -1. Now the third pKa then is where we begin to lose the hydrogen from the amine group, from the alpha amine group, and that's going to be our pK3 or our pKa3. And that's when we've added 2.5 equivalents of our base. We're going to hit that pKa, and when we reach 3 equivalents of base, we will have deprotonated all of the dissociable protons, because this is a strong base weak acid dissociation. So we have negative charge here, neutral here, -1 here, and that gives us a -2 on the molecule. Okay, next we're going to look at lysine. So which protons do we have coming off when? The first one we're losing is this one. I don't know why I'm not able to draw here. Hang on. This one. Okay. What do we lose next? Next we're going to lose one of these. Okay, that's going to be our pKa2. And then finally we lose one of these, which is going to be our pKa3. Okay, so that's our pKa1, pKa2, and pKa3. So when we reach 2 equivalents of the base, of the strong base that we have added, okay, then we will be at our isoelectric point, where we have this positive charge here balancing out this negative charge here. Okay, so you're at the isoelectric point when you have equal charges. Alright, and so balancing each other out. And so in the final species is going to be -1 charged. So it's important to understand the structure of all of these amino acids. What is the pH of a solution of glutamic acid if the alpha carboxyl is 1/4 dissociated? Okay, so we've got glutamic acid. Okay, and so let's draw glutamic acid actually. Let's go ahead and draw that out. And so we've got our, remember, amino acid looks like this. And we're going to start out with this species, and our R group for glutamic acid is, let's just kind of draw it. Like this. Okay, and it's connected here. So this is our R group for glutamic acid. And the alpha carboxyl then is going to be the first one that is going to come off. Okay, so what is the pH of the solution if the alpha carboxyl group is a quarter dissociated. Alright, so how do we calculate that? The pH is equal to the pKa plus the log of A minus over HA. Okay, and so remember, this A minus over HA is a ratio. You can use moles, you can use molar, it doesn't really matter. We know this is a quarter dissociated, so what does that mean? It means that 1/4 is dissociated and 3/4 is not. It means we have a 1 to 3 ratio, but we can write it like this. We can say, let me get a different color. We can say we have 1/4 over 3/4. Okay, and then our 4's are going to cancel, and that's going to give us log of 1/3. Log of 1/3. Okay, so that's pH is equal to 2 plus negative 0.477, which is equal to 1.523. So we can calculate that pH like that. So what is the pH of a lysine solution if the side chain amino acid is 3/4 dissociated? So we can say that if it's 3/4 dissociated, then we have 3/4 in the A minus, okay, and then 1/4 in the HA form. So the 4's cancel, and that gives us log of 3 over 1. So the pH is equal to the pKa, which is 10.5. You can look that up for this group. Log of 3 over 1, which is 0.477. So our pKa is equal to 11. Okay, we'll do some more calculations for this chapter in the later videos. And thank you for watching, and I'll see you next time.